Hello, welcome to Designs for the Edge with Microchip Technology. Designs for the Edge is our ongoing live stream series in which we talk about market trends and system design challenges. We are live on LinkedIn, YouTube, and Facebook. Feel free to enter your comments and questions into the chat, and please like and subscribe as appropriate. On to our topic for today, time-sensitive networking. I'm your host, Eric Latfelter, and joining us remotely is our subject matter expert, Emil Piper. Emil, welcome to Designs for the Edge.
Thank you very much, Eric, and thank you for inviting me. My name is Emil Piper, and I'm based in Copenhagen, Denmark, together with the Microchip R&D for Ethernet technology. I'm a manager of a curling team. It's a specialized team of solution engineers focusing on Ethernet technology. We help our customers R&D with the design process and are participating in the design process, resolving some of the issue if they have them at all.
Great. Well, thanks. We're glad you're with us. Time-sensitive networking is a pretty complex topic. So for our viewers today, we're going to start with an introduction to the topic. We'll go deep into some of the functions, and then at the end, we'll wrap up with some of the solutions that Microchip provides. Emil, to start us out, would you give us an overview of what is the state of the art of Ethernet technology today?
Yes. I would start telling you that what I'm going to talk about today is a 2-hour masterclass I did in Berlin some weeks ago, but I am asked to do it this class in 30 minutes. So I will be quite quick, and I will only take the most essential to understand. So this is mostly to understand this deterministic networking and make it clear for other people what it actually is. I will only go through some of the standards, but to start with, I will like to make you look at this picture. This is a road with a lot of cars, and I'm gonna do this analogy for the understanding with cars. So in the picture, there is a lot of cars. There is a lot of intersections here. So every intersection here I will call a switch, and every car will call a frame or frame stream. And there's lots of different cars, and that's the same in Ethernet. There's a lot of different types of frames. There's jumbo frames, there's small frames, information frames, there's VIP frames. So I will try to explain what TSN is using this analogy. But why do we really need deterministic networking? Yeah, today, as we see it, if there's no cars on the road, if there's very, very few traffic on the lines, cars on the roads, then there's no problem. Then we don't need extra special features to do this. There's no problem there. But when we are going to stream stuff from the Ethernet and using IT technology for streaming, or for it really quickly gets congested. So when the Ethernet today without anything, then you will only get 30 to 40% throughput, and this is not very acceptable, especially not if you have frames that needs to go to the address. And I'm gonna take some case examples first to show you why we need this TSN features. And also we can increase the bandwidth. That the same analogy as a sort of widen the road, meaning we can send more cars through the road, but we cannot just keep doing this. So maybe we should apply some features to make it more controllable. So TSN is more like get control of the network as we see it today, get it more deterministic, so we can pack the frames more tight, and also make it more reliable. Especially, maybe we should take the next slide. All right. Yes. So there is everybody knows what IT is. This is informational technology, or informational traffic, as I call it. And that's, everybody knows about that. This is used when you're sending emails. This is used when you're streaming Netflix. This is used when you're calling a person on WhatsApp, for example. But there's also something called OT. This is operational traffic, or operational technology. And this is what they have been doing in factory settings. Just to take one example, I can come with a lot of other examples, but I'll just stick with this one. In factory settings, it's really, really important that you get the frame or the car from the sensor to the robot arm, or whatever it needs to go, from the discovery to the actuator. So we cannot just rely on 30 to 40% of throughput here. So this is what factory automation has done that for many years now. It has just been proprietary protocols for data transportation. Maybe they're using Profinet or EtherCAT or something else. There's a lot of other standards here, but right now, so they have been using sort of a parallel communication system to drive all this factory communication. But there is more and more data coming through, and there is also a demand on running IT and OT on the same system, because then you only need one system. You don't need two parallel systems in the factory automation. So it will get it a lot cheaper. So this is why we have made a couple of standards, the TSN standards, to make the factory setting more deterministic when you're using a normal standard Ethernet.
Okay, so while we're mentioning the standards, just to clarify, so I want to ensure I understand, this is a set of standards that is basically additional to the existing Ethernet protocol. Doesn't replace it, yeah, but adds some sophistication to it.
That's correct. There's the IEEE. This is a standardization forum, which is one of the biggest companies like Ericsson, Nokia, Cisco, and Microchip are participating in, to make sure that the new standards is, of course, standardized. So all the switches and all the Ethernet technology can talk with each other. Yep. And if we're talking TSN components in the common standards, then it's divided in 4 different chapters, or 4 different categories. That is synchronization, and there is latency, and there's reliability, and then there's resource management. And I'm going to take some of the features from synchronization and latency and reliability today. Okay. To explain those.
Okay. Yes. So IEEE is the standards body overseeing both Ethernet and the TSN additional protocols.
Exactly. Okay. Exactly. There is other standardization companies or forums like Avenue. Those guys are more or less taking care of the testing standards, how to test this. Yeah.
Okay. All right, so let's start looking at some of the additional benefits of time-sensitive networking.
Yes. as I showed you before, there was a lot of roads, there was a lot of intersection, there was a lot of cars. So here again, I'm taking the first standard. This is the TAS, time-aware shaping, and this standard, this standard is quite interesting because it's basically just to add some traffic lights to the Ethernet. Imagine that there is no traffic lights, and then imagine how much chaos that there could be on the lines if there's no traffic lights. So let's just add some traffic lights and then divide it into sort of two sections. We are using the principle as the time division multiplex axis. This is TDMA, which you probably know from mobile phones and other technologies. And this is very, so you slice up the sort of when the different the different cars are allowed to attend the lines or the roads. So we get more control here. In this case, as you can see on the left-hand side, we have divided, made some special time slicing for VIP frames. This is the red one, and the yellow one is for best effort traffic. So let me just point out to start with here that you don't need to run TSN on the whole traffic. You can, it can just be some of the traffic that needs to run the TSN technology or the TSN features. So in this case, of course, you run the TAS, works on all the frames, but you have time sliced, some for TSN traffic, the VIP frames, and some for normal traffic. And what we want from this is to avoid congestions. We want to take control of the Ethernet and make sure that everything is in very nice order. Maybe you can take the next slide. Yes, this is where we sort of exaggerated a little here, just to be able to measure it in the Wireshark. And so we made this open time slot for 1 millisecond, and then we closed it for 9 milliseconds. So it would be easy to see on the graphs. And then we disable in our switch. We disable the TAS, time-aware shaper, and then we get the other picture in the right-hand side in the bottom. So this is a little bit more chaos, and you can also see it exceeds the bandwidth a couple of places, and there's a couple of places where the lines are idle. That's nothing happening.
Yep.
So maybe we can utilize this somehow. So let's take the next slide.
We have much more predictable traffic just with that shaping.
Yes.
Okay.
Exactly. Yeah, it makes more control on this. So the fundamental of this to do this test, to do this time slicing, it's also important that all the switches and all the routers have the same concept of time. And to do this, we can implement another TSN feature. This is time synchronization, and this is the S2EP6 time stamping. So this makes it very accurate, and this is the AS standard. And as you can see here, there's some cars. This is small time cars that goes from one switch to the next switch. As again, I make this analogy as cars. So every car is a frame. So it's a small time frames, and every intersection here is a switch. So even though that you have the same frequency on all the switches, you might have a phase differences in the switches. So we need to align this, the phases between all the switches, and we can do this by driving some small time cars or frames to one up to the next one and measure the delay, and then one back, and then one again. Maybe the next slide, Aaron. Yes, here we can see the synchronization model here in the left hand side. So this is just we can measure the delay from the first two, send two messages, T1 and T2, and then we send the T back. We send the receiving switch says, okay, I got this delay, and then we set a follow-up frame as a T4, and this can make very, very easy calculation. You can sort of make the time difference, so you can make you know what the offset is, and then you can do the offset, and then you can phase align the switches towards each other. And on the right hand side here, you can see here we have two switches, one PBS pulses from two different switches. This has been phased aligned using this time IEEE 1588 synchronization model. So, next slide, yes. So, we need also to make some delay reduction because there's a lot of frames, and sometimes within our time slicing that we talked about before, the test, we can start up a jumbo frame. For example, this is a big truck over the buses here, and if we then need our VIP frames here, as my analogy says here, it can be police cars or ambulance, fire trucks, and so on. So this is not very convenient, because if you already started up a big jumbo frame on the line, then there is no way you can. The VIP frame basically have to wait until it gets on the time. But if you sort of implement this frame preemption, the QBU standard, then we can stop the jumbo frame when the VIP frames needs to go in. We can stop it in the middle of the sending. We can send out the VIP frame, and we can just continue the frame, the rest of the jumbo frame. And of course, this needs all this. The switches need to be frame preemption enabled and have this capability.
Okay, so again, these are high priority frames that might likely have to do with safety in a vehicle, or a robot, or security, or things like that.
Yes, imagine the first case that I came up with. This is the factory automation. If you think about the best effort traffic, which just maybe one of the guys is doing a report or sending a mail in the system, then it doesn't really matter how delayed that is. But if there is a sensor that sends that this particularly device on the conveyor belt is wrong and needs to be picked up and thrown away, then it really needs to get this message to the robot arm or the device, the actuator, and that throws this away in a reliable and certain way. So the Ethernet here needs to be so much in control that you can rely on this. You have to know when the frame is arriving in the factory automation. Okay. Also, maybe if we take another case example, if you take your smart home, for example, just that something everybody knows about, it's very unimportant that maybe there's some holes in the music, or the Netflix is there's some holes in the data here because it's buffering anyway. But if you need to turn on and off the light, it's just very annoying if you have to push the button 3 times until the right frame gets to the right bulb or the right group of lights. I have in my home, I have sort of grouped a lot of lights, and sometimes I can see I need to press 2 times to get all the lights turning on, and that's very annoying. So I think I could benefit by implementing TSN technology in my smart home.
Okay.
Yeah, it's a bit nerdish, but
Right.
yeah,
Good.
so,
Okay.
yeah.
Okay.
Yes. Next slide, maybe. Yes, this is just the frame preemption again. So if we look at the picture in the top, this is without frame preemption enabled. So here we have a high priority. This is the red frame, and we have a low priority. So if we look at the time-wise in this, the low priority is a jumbo frame, for example. It's much bigger than the red VIP frame, but it has already started to transmit on the line, and then the red one has to wait until the line is transmitted, finished, or the lower priority is finished with the transmission. On the bottom here, in the bottom example, there's a high priority here. And the low priority and the frame preemption is enabled. And here you can see we started again with the low priority frame started up, but then we sort of stopped the transmission of the low priority, and then we allow the VIP frame to get in between, and then we just continue transmit the rest. And then you can all of a sudden see there is a latency improvement here.
Okay.
This is some of the features that make the Ethernet more in control and more reliable, and also for some part of the data frames more faster.
Okay. Great.
So next slide. Yes, here. So this is also a feature that Microchip has implemented in our switches, and this is actually not a standardized feature. IEEE is working on this, working on implementing this, but it's quite hard. But we have sort of implemented our version of the cut-through. And here you should imagine, again, 2 switches or a lot of switches. I'm just drawn 2 switches here, and we have all the traffic. But every car or every data frame is stopped it's stopped, and it's stored, and it's done a lot of things here. And then you need to check it. This is the CIC, which is on every frame. This is kind of a passport all the frames has, cyclic redundancy check, and you need to stop the frame, and you need to store it, and then you need to check it, and then you can allow it to go further. So in this case, if you just remove this checkpoint on all the switches, you can more or less have a green, and you synchronize all the frames, all the switches here. Then you can more or less have a green light. It's sort of like driving in a city where there's a lot of traffic lights and lots of intersections. And every time you get to the next intersection, there will be a green light, and there will be no checkpoint. There's no policeman to check your passport every time. So you can just run through the whole city in a very convenient and reliable time. So remove the checkpoints. It's much easier. The negative part on this is if you have some unwanted traffic, or you have some traffic that is not valid anymore, or maybe the frame has been damaged somehow, you'll still have to transmit it all the way up to the address and or the receiver, and then it will discard it in the end. So there will be a little bit more traffic here, but in the end really make a delay reduction in the system. Next slide. Yes. So the TSN feature is, as I started to say, this is a lot of different features. You don't need to implement all the features at once, but this feature is also a very nice feature. And this is the PS stream and filter policing. And this is, let me just see here. Yeah, this is in the category of reliability. So in order to make the Ethernet more reliable or more streamlined and more in control, I call this a 12-road gateway entrance, and we have several lanes we can put the different traffic in. So the peer stream filtering and policing will prioritize and sort all the incoming traffic. So this is in the input of the switch, of the ingress. So it will put Jumbo frames in one lane. It will put a normal best effort traffic in another lane, and it will put VIP frame in some lanes. And there is basically 8 traffic lanes. I've just took 3 just to get an overview,
right?
Not to get the slide too busy, but it will. There is 8 lanes in total normally on this feature.
So 8 ways to categorize the frames.
It's for categorizing. So we can get sort of a stream of the same type of cars or frames out. So this would be much more in control. We can utilize the time. We just in one of the first slides I showed you, there is a VIP time frame in the time slice. Maybe we can send more than 1 car, so it's very nice that we have 3 cars, or maybe you have 10 cars, maybe you have 100 cars we can send in one at that time slot.
Okay.
So that's very nice to have this categorized and sorted and prioritized. So the next frame, next slide. So this is the 12-road gate exit. So we also need to get out of this. We need to have a feature that allows us to get this out again to the line. So this is the credit-based shaper, and this is also called the CBS. And this keeps track of the transmit order. It's a sequence. It's a liquid bucket principle we're using for this, and this is basically control all the streams and prioritizing them and assign them to the right lane, and also assigning the bandwidth or the time slot, or how much bandwidth do we need for this particular stream. So yeah, you all want to know, we can also use another analogy. If you're waiting for the ferry, there is different lanes you are in. You have all the trucks in one lane, you have all the guys who paid a lot of money to be first priority in one lane, and then you have all the stragglers who's coming in the last minutes in the different lanes, the other lanes. So yeah, so this is basically the principle. In the middle of the picture here, we see some graphs. So I have drawn a sort of a dotted line. This is the bandwidth maximum, that the maximum of capable on the line. And we can see here, if you're not applying the CBS TSN feature, that might be some boost effect on the line. That must be some very, very congested times. So all this boost over the bandwidth line will basically not come through. So we need to resend all those frames there is at that time part. And then there is some under the line. This is where the line is not congested. This is where they're idle. So why don't we try to put all the traffic that is over the bandwidth and put them down where there is actually room for it. So what we want is to get the graph below as sort of very, very idle or very time
so
steady.
Yes, steady. So
at
the end of the day, we want a steady transmission rate, so that gives us the most effective use of the existing bandwidth.
Exactly.
Yeah. Okay.
Yeah. So again, it's a matter of control. It's a matter of making something deterministic, reliable on the line. So maybe we could take the next slide.
Of course.
Yeah. Here we try to measure it. This is the credit-based shaper. You see in the top graph, there's no credit-based shaping enabled, so we get the bursts. So that's not very good. And in the bottom graph, we enable the CPS, so we try to run the same type of traffic, and you can see there is a lot more steady traffic here. Next slide. Yes, this is a very neat feature. This is also for reliability. This is the frame replication elimination for reliability, the FREYR version. And to go back to my analogy with the cars, here we have here I actually put 4 different intersections, which means 4 different switches, so I can make a sort of a mesh network. So FREYR is to use the analogy, I'm using 2 different courier services. I put the package in the same package in both courier services. So you're using TNT and GLS, for example, or what you have in your country. And then you make sure that it runs 2 different paths to the address or to the receiver. And when it then receives both packages, then it just throws away the last one.
Okay.
It's very simple, very neat, and I think this is, in my belief, this is the superset of redundancy. There is other legacy redundancy. There's PIP or HHR, which is ranked topologies or parallel networking. So in this case, I would say that that FREYR is a superset because this is a mesh-based, stream-based, where the other one is port-based, and this is much easier to work with, and you can also, but you can still run the legacy standards as a virtual together with this one. So
okay.
So this is not one or the other. You can use both of them if you like.
Great. Well, thanks for that walkthrough. I can see the added value of each one of these, and thank you for the great analogies with the traffic. There are a lot of nuances there. So how does Microchip help system designers get started with Ethernet design and TSN in particular?
Well, normally we do an analysis. My team is a solution engineer, so we do an analysis on what is the need of the company and where is the company, which state is it in, what is the potential. So we do a lot of thinking, and then we come up with some solutions for the particularly need the R&D in the company has. And then we have a lot of technology here in Microchip for this, particularly for this TSN technology. And as you see here on this slide, first of all, if I start out with the left-hand side, this is some legacy switches we have. This is the Spark 3 and the SPARX 4 switch cores, and they're very nice. They're very popular. This is what we had in the previous time. And then from 2020, we came up with this SPARX 5 switch core, and going forward, this is the SPARX 5 switch core is based in all those switches here. And then there is different topologies in the switches. Okay. The SPARX 5 switch core here in the middle of the picture here is the first one, and is our superset. It has up to 200 gigabit bandwidth, and it has 64 ports, and is able to run up to 25 gigabit CERT ports. So this is the superset. Then there is the other switches here. This is a subset. For example, we take the Laguna in the right-hand side in the top. This also comes in different varieties and scalability, but it has only 24 ports, and the port can only go up to 10 gigabit, but for many solutions it is enough. It's a smaller chip. It's still based on the same switch core, but the microprocessor inside is a little bit smaller. Okay. Yeah, of course the service port is less, and also the bandwidth, as you can see, the maximum bandwidth here is around 100 gigabit. We also have our Maserati. This is also in the right-hand side in the bottom. This consists of very specialized for factory settings, but we also found out that this could be used in many other varieties in military and aerospace, also commercial airplanes. So this is quite interesting. So this is a low port count switches. This the LAN 9668 is an 8-port switch, and the LAN 9662 is a port switch, and there is a built-in two 1 gig ports inside, PHYs inside, so it would be easier to make daisy chain on those switches. The 4-port switch is an endpoint switch, so it also has a real-time engine, which is a sort of a, if I should use the same analogy as before, so this is a train station where you can put data in and out more or less in real time. Okay. So maybe you could see the passenger can hop on and off the trains while the train is still running. So this is a real-time engine. So this is very sexy in the factory automation settings, or maybe in a military combat vehicle or other. We also have a whole other department. So I told you I was based in Copenhagen, where we have the R&D for switch and switch management technology, but in Karlsruhe in Germany we have all the automotive, and this technology of course also have TSN technology built in. So this is the T1 and T1S single pair Ethernet that we have in the middle here. So this is just an example on our switches. We also of course have PHYs, and we have TPLLs, and we have a lot of other technology we use within TSN technology.
Right. So,
and of course, yeah.
Yeah. So just for the switches, can you talk us through the software stack, and then what Microchip offers there as well?
Yes. We have different options on our switches. So we would like to we have made this iStacks, which is a superset of our stack software. And if you don't need all our features in our superset, then we also have some subset SMB stacks and web stacks,
right.
depending on whatever features you need on the switches. And unfortunately, this is quite an expensive software because we have a very, very large team in Copenhagen doing new feature sets and new developing all the time. And also, if we discover that some of parts of the stacks need to be changed, we can also do this very quickly in Copenhagen. So this comes with a license, but also many companies want to build their own stack software or maybe have their own stack software. So here we can offer any API driver version. This is the Mesa MIPA, and we have some for the Profinet that only works on the Maserati project. And also we have some features based in the MP Lab, and this is software you can download from the net, and the API you can download from the Microchip website.
Okay.
All the software is Linux based, so this is the OS on all the chips, and all the switches here are having an internal microprocessor. Our supersets chip has an ARM 53 dual core 1 gigahertz microprocessor inside to run this management software. And this is only for the management software. We do all the hard work in the switch core. All features we have, all the switch features we have is done in the hardware. So we don't cheat. We don't put the streams up in the microprocessor and do some features there. So everything, all the hard work is done in hardware.
Okay. So again, a lot of choices with hardware.
I just have one more feature
to
tell you about. This is the switch staff, and this is the Linux standardized way to access the hardware from the software. So the switch step is also for free, but we do this on our Box 5 and going forward with all our switches from now on. The switch step solution is basically if you have your own stack software and you have built this interface yourself on your stack software, so it would be easy for you to go from, for example, some of our competitors' switches to easy to change it out with our switch, Microchip switch. So the mitigation would be quite easy.
Yeah. Okay. Okay. So again, a lot of hardware choices, a lot of software choices and nuances. Can you talk about any development systems or evaluation systems that our clients can use to just make their evaluation or development a little easier?
Yes. So those features here makes it quite easy to be a solution engineer like us. So we have actually pre-done our cake, so to speak. So we've done not a lot, but we do 2-3. There's very little reference designs with our new switches and our old switches. So we have this reference design, and all our reference designs also corresponds to an evaluation board you can buy on Microchip Direct. So in the left-hand side, there is an example here. This is the Maserati. This is the LAN 9668. And on this reference design, we have two of our quad PHYs on. This is the LAN 8814. You can see two of those. And then we have we have this Starlink DPLL. This is our Azerite DPLL from Starlink. The ZL30772, and those R&D is in Canada, and we're working close together with those guys as well. So you can see here we have all of this, and we have tested this in our R&D in Copenhagen, so we know that it works very good. So in the left-hand side, you can see there's a schematic. So, and there are some layout files, and there are some stencils. So all this we can provide to you when you start up the project. We provide this to the company R&D, saying you can utilize this. You can take our schematic. You can steal whatever you want. You can have the ORCAD file. You can have the base files. Just steal whatever you want. Whatever makes it work for you in your own R&D. So that some of this makes it much easier to go to some of the milestones in our customers' R&D design processes. We also have a table of contents. We have the full bill of materials we can provide with you. We have, this is, as you can see, the switch files, DPLL, PoE, power, memory, all sort of things we can put together for you. So we already have a finished system. So if some of the reference designs apply to just remotely to what project you have in the company has in mind, this is quite easy to check this out. And we also have, as I said before, the software options. We have a turnkey solution. This is our stack software. As I mentioned before, we have a ticket support system. So this is, you go into Microchip and then make a ticket, and then some of our guys will look into this. Okay. And if we and my team is working together with this R&D, we will get the ticket also on our table, so we will sort of hand carry the ticket. If we cannot answer this, we'll use our R&D and our business unit here in Copenhagen, or in the Fire R&D, or in Canada, or whatever R&D we are talking about, and ask them to sort of to look into the issue that the company R&D have. We also have other documents. We have a Microchip solution, so you can actually send your schematic in, and we will try to do a micro schematic review for the customers. We also can provide a hardware check manual. That's usually what we ask the customers to do. So this is a checkout manual, so we go in very, very detailed in this. So have you remember this resistor here? You have this bleed resistor here. Do you have this capacitor here? Is it the right value? Do you have the VS here close to the ground point, and so on? And it's a very, very detailed hardware checkup design manual.
Okay.
For the switches. So this is some of the things we like to provide that help us to get to the customer, for the customers to get to their milestones quickly.
Right.
This last slide here is just to show we have different kind of evaluation boards that relates to our reference designs. So in the top we have this VSC 7558. This is the superset of our Fox 5 engine, switch engine, and then we have the Laguna. This is our newest industrial switch, which can also be utilized for many other areas than industrial, we found out. This is the LAN 969X, because there's 3 versions. There's actually 9 versions, but that's not go into details. Yes, and then in the bottom we have this LAN 9668. This is our Maserati 1 gig TSN switch, the small one. Just to show that we have actually those evaluation ports.
Right.
I think the Laguna comes, we're about to come out with a automotive version, which is quite fast boot up and with T1 files on this, and also some T1S files as I remember. So this is quite interesting, but this is new. It's not on the web yet, but it will come.
Okay, so we've covered a lot of material there. You just mentioned the web. If somebody wants to go to our site and find an overview or look for details on any of this time-sensitive networking information, what's the best place for them to go to?
Well, to start with, I would just go into microchip.com, and then in the search area, just search for TSN, and then you'll get the first option there. Click on that, and then it will guide you and explain to you whatever options we have, and then then go from there.
Okay.
To see whatever chips we have, and then I will advise you to contact maybe Microchip if you are a little bit larger company. Then we can engage if you have a problem with a solution, or and your opportunity is large enough, then we can engage with my team, and our client engagement managers can engage, and we'll go in and have some different interaction with you depending on which company you are. And I think I may fail to say that my company is not my company. My team is shut down all over Europe, and we will more or less engage in R&D, like our customer R&D in all EMEA.
Great.
With all different kind of Ethernet and TSN technology.
Okay. All right. Well, thanks for that. Thanks again for the entire walkthrough. I really appreciate the overview. I appreciate you sharing your expertise. At this point, we'll take a couple of minutes, go to the tablet and see if we have any questions from the viewers today. Bear with me one moment. So a couple of questions queued up. First question is, Emil, are there any special security requirements for TSN?
No, there's initially nothing. TSN has nothing to do with security. So both Fabric security and TSN are considered as independently on each other. But if we're talking security, we have options for MACsec, which is encryption of the data line from the files, and we're also coming up with MACsec built into the switches. That is in our roadmap in the future, and also secure boot is some of the secure features that has been implemented in our TSN switches.
Okay.
So we have solutions for this.
Separate solutions for security. Okay. Next question, short question, but is TSN layer 3 compatible?
No. TSN is a collection of layer 2 Ethernet services, and it doesn't need layer 3 actually. So.
Okay. Next question, can you use unmanaged switches or media converters in a TSN network?
You can only use media converters if there is hardware is TSN capable, and they participate in the TSN network. You cannot use unmanaged switches, so you need to sort of, if you take the decision to make a deterministic network, then all the components needs to be a TSN or deterministic.
Okay. All right. So a couple of questions about the TSN network here and the equipment. Do you need special passive network components, such as a special cable for TSN?
No. This is the TSN features standards. running on standard Ethernet, so it's just the same architecture as existing network cable be used, and yeah, for data radius of 1 gigabits and above, you have to use the gigabit capable cables, of course, just like normal Ethernet. So in other words, 8 core copper cables or gigabit FO cables is required on this, but this is also goes for normal Ethernet.
Okay. All right, and last one, kind of a very similar question. Do you need special Ethernet processors for TSN, or do today's standard Ethernet components also work?
Well, a TSN capable hardware block is needed for TSN.
Okay.
So the current installed Ethernet blocks generally cannot be expanded by software to include TSN functionality. So it's possible to run other protocols on the TSN, like Profinet. That means that in our switches, as I said before, we have most of all of our functionalities run in the hardware. You can go in and do some streaming up to the microprocessor and do it, but that's a very, very bad decision.
Okay.
Or a bad solution. But yeah, I wouldn't advise to do this.
Okay.
So no, the answer is no. You need a specialized cross Ethernet TSN.
You need to go to microchip.com and type in TSN into the search box and look for a new solution.
Yeah.
It sounds like. Okay.
Exactly.
All right. Emil, let's leave it there. Thank you again so much for your time. To our audience today, thank you for your time, and thank you for joining us on Designs for the Edge. This is the last episode of our second season. You can visit us at microchip.com/designsfortheedge. You can peruse our previously recorded sessions from that site, and you can sign up for notifications for our next season. We'll be back in 2025. In the meantime, if you like this format, please check out microchip.com/coffeebreak. We have an ongoing live stream series there where we talk about new products and solutions and all manner of things in the electronics industry. I think we're kicking off our next season next week. So check that out as well. Thank you so much, and I hope to see you next year. Have a good day.